Okay, let's unpack this. Think about how quickly you learn something new without um, instantly forgetting everything you already know.
Right.
Like meeting a new friend, you instantly recognize their face and learn it, but somehow you don't suddenly forget the faces of your family and your other friends.
Yeah, it's automatic.
Our brains just do this rapid, ongoing learning, constantly integrating new information while keeping the old. It's pretty astounding when you stop to consider it.
It truly is. And that incredible capability points directly to one of the most uh, fundamental puzzles in understanding the brain and cognition,
Yeah.
the stability plasticity dilemma.
The stability plasticity dilemma, right? So how can the brain be plastic, meaning it's incredibly adaptable, capable of learning novel things fast,
Right.
but simultaneously be stable, retaining vast amounts of previous learning without simply overwriting it?
Exactly. It's a challenge many artificial systems face. You train them on new data, and they undergo what's called catastrophic forgetting,
Right, wiping the slate clean.
essentially wiping out old memories. The brain, thankfully, seems to have, figured out how to avoid that.
And that's the core problem that adaptive resonance theory, or RT, proposes a solution for. Is that the idea?
That's right. RT is a powerful cognitive and neural theory developed by Stephen Grossberg, and it offers a really detailed account of how the brain can learn continuously and stably in a changing world.
Okay.
It describes mechanisms for attention, categorization, recognition, prediction, a lot.
And our guide for this deep dive is a comprehensive look at art from the source itself, a Scholarpedia article written by Grossberg.
Yeah, it's a fantastic resource. Really lays out the core ideas, the proposed brain mechanisms, and the broad implications of the theory.
So our mission today is to dig into this article, really try to understand the stability plasticity dilemma, explore how art suggests the brain solves it, and see how these proposed mechanisms connect to things we experience every day, like paying attention, remembering, and maybe even being conscious. Let's jump in.
Great. So, elaborating a bit on the dilemma, we are immersed in a constant stream of non-stationary data. The world keeps changing around us.
Right, nothing stays the same.
And much of our learning is unsupervised. We're not always given explicit feedback or labels. The brain has to figure out how to make sense of this, learn quickly when needed, and crucially, integrate it without forgetting the vast library of information it already holds.
So how does art propose the brain achieves this balancing act? What's the sort of fundamental approach?
Well, the theory posits that this isn't solved by just one single mechanism, but through the dynamic interaction of several key processes.
Okay.
The source uses the acronym CLEARS to summarize them: consciousness, learning, expectation, attention, resonance, and synchrony.
CLEARS, clears.
Exactly. And the prediction is that any brain system, biological or, even artificial, that solves the stability plasticity dilemma will rely on variations of these CLEARS mechanisms.
Clears. That's helpful. And the theory makes some pretty bold claims, doesn't it? Like
Yeah.
connecting these learning mechanisms to why animals are intentional, why we pay attention.
Absolutely. It suggests these seemingly disparate functions are deeply intertwined. And importantly, it makes a core prediction that all conscious states are resonant states.
Wow. Okay, that's big.
It is. That's a profound link between a specific brain dynamic resonance and our subjective experience. RT also explains how brains can learn different kinds of information mappings.
Zappings, like,
Like many-to-one, which is essential for recognizing something like a chair from any angle, or one-to-many, allowing you to know many different facts or properties about that one chair.
okay, so it's about building rich, interconnected knowledge, not just simple labels.
Precisely. It's about building understanding in a dynamic environment.
Now, the brain isn't just one big homogeneous blob, right? The source talks about different complementary streams of processing. RT, as a theory, focuses primarily on one of these streams.
That's right. It introduces the idea of parallel complementary processing streams. RE largely describes the mechanisms operating within what's known as the what stream or the ventral stream.
The what stream?
This part of the brain is heavily involved in perceptual and cognitive processing, recognizing what things are.
Okay, the what stream. And how does the learning happen in this stream, according to Art? What's the mechanism?
This stream relies on excitatory matching and match-based learning, and this is the critical part. Match-based learning is the proposed mechanism that solves the stability plasticity dilemma for recognizing categories. It allows for fast learning without catastrophic forgetting. That's why you can learn a new friend's face so quickly and clearly without confusing it with or erasing memories of other faces.
So this stream is about building stable, invariant categories. Things that stay the same even if they look a bit different.
Exactly. It learns invariant categories the ability to recognize an object regardless of variations like size, position, or viewing angle. The source points to the inferotemporal cortex as a key area where this kind of invariant recognition occurs. This type of learning is also closely associated with declarative memory.
Declarative memory. That's like facts and events.
Yes, the memory for facts, events, the kind of learning that we can consciously recall.
And if the theory predicts that conscious states are resonant states, and RT describes learning in this stream, does that mean the declarative memories formed here can be conscious?
That's the connection the theory makes. The proposed resonant states in the what stream are hypothesized to be the neural basis for conscious recognition and the subjective experience of declarative memory.
Right, so that's the what stream focused on stable identity and recognition. But you mentioned these streams are complementary. What about the other one?
That's the where stream or the dorsal stream. This system is geared towards spatial processing and motor control, figuring out where things are and how to interact with them.
Okay, where and how. And the learning rules here are different.
Fundamentally different, and for a really interesting reason. This stream uses inhibitory matching and mismatch-based learning.
Mismatch-based.
Yes, and unlike the what stream, in the where stream, catastrophic forgetting is actually desirable.
Wait, desirable? Why on earth would you want to forget catastrophically when learning where things are or how to move? That sounds dangerous.
Well, think about it. Because our bodies are constantly changing.
Oh, right. Growing, aging.
Exactly. Think about learning to walk as a baby versus running as an adult, or adapting your tennis swing as you get stronger. Your motor commands, your sense of where your limbs are in space, need constant, rapid updating.
So the old way of moving isn't just useless, it gets in the way.
Precisely. Old motor parameters actively hinder current performance. You need to essentially overwrite or forget the old to adapt quickly to your current body and the task.
Okay.
The source uses the example of generating a motor command to move your arm. You calculate the vector difference between your current position and the target position. That's based on mismatch or difference, not matching an existing pattern.
So it's about adaptation and continuous recalibration rather than building stable, permanent memories. Makes sense. And this relates to a different type of memory, too.
Yes, this type of learning is linked to procedural memory, the learning how that governs skills and habits, like riding a bike.
Right. Things you just do.
Exactly. And crucially, because this stream relies on inhibitory mismatch rather than excitatory resonance, the theory provides a potential mechanistic explanation for why procedural memories like how to ride a bike or type are typically unconscious.
You do them, but you don't consciously recall the steps in the same way you recall an event.
You got it.
That makes a powerful distinction. So the brain isn't just one system learning everything the same way. It's this dynamic interplay between two different specialized learning engines, one for stable identity, conscious, and one for flexible action, unconscious.
Exactly. And neither can function effectively without the other. The interaction, the source calls it what-where fusion, is what allows us to use our recognition of what an object is to guide our actions where it is in space. RT, as the source notes, is primarily a theory of the what stream, and understanding this complementary organization is key to appreciating its scope.
Okay, let's zero in on that what stream again and how attention and expectation work in detail. You mentioned top-down expectations playing a role. How does having an expectation, like, say, looking for a yellow ball, actually influence the incoming sensory data?
It primes the system. When you have an expectation, it sends top-down signals down to the lower levels of processing. This leads to excitatory matching with the incoming bottom-up data.
Meaning
If features in the input match what you expect, those features are amplified and processed more strongly, made more salient.
Okay, so expectation basically biases the system towards finding what it's looking for. Turns up the volume on expected things?
Precisely. And importantly, if there's a mismatch between the expectation and the input, the unexpected features can actually be suppressed.
So it turns down the volume on irrelevant stuff, too.
Exactly. This effectively focuses your attention. You're filtering out what's irrelevant based on what you expect to see or hear.
That's really interesting, that attention isn't just about enhancing. It's also about suppressing, based on internal states, on expectations, and this matching process, when it's good enough, leads to the formation of resonance.
Yes. When the bottom-up input matches the top-down expectations sufficiently well across different levels of processing, say, from basic features up to a recognized category, positive feedback loops between those levels become active.
Like an echo chamber.
Sort of, yeah. This amplifies, synchronizes, and prolongs the neural activity in those circuits. That sustained, amplified, synchronized activity is the resonant state.
And what's the job of this resonant state? Why is it so important in RT?
It does two critical things. First, it's what truly focuses attention on the critical feature pattern, the specific combination of features in the input that are consistent with the recognized category. It makes that pattern really pop out, become salient.
Okay, and second?
Second, and absolutely central to the theory, RT predicts that only these resonant states are strong enough and stable enough to drive fast, stable learning in the adaptive weights.
The long-term memory connections.
Exactly. The long-term memory connections between processing levels. Resonance is the signal that says, okay, pay attention. This input is meaningful, it's consistent with something I know or need to learn, and it's worth strengthening the connections related to it.
No resonance, no learning.
Essentially, yes. No stable, fast learning without resonance.
And this brings us back to that really big hypothesis you mentioned earlier. All conscious states are resonant states.
It does. The theory proposes that these resonant states are the neural correlates of consciousness. The sustained, synchronized activity is what underlies the subjective experience.
And different kinds of resonance mean different kinds of conscious experience.
That's the idea. Different types of resonant interactions happening in different brain areas could correspond to different kinds of conscious experience. The source mentions examples like surface shroud resonances relating to the conscious experience of visual qualities, like color or texture.
Quote.
Right. Feature category resonances for object recognition, item list resonances for speech perception, and cognitive emotional resonances for feelings.
That's a really elegant theoretical link between a specific dynamic process, resonance, and our subjective experience. So structurally, how does the brain implement this top-down attention and matching process that leads to resonance? What's the mechanism?
The proposed mechanism is called the ART matching rule. The source describes it as a modulatory on-center, off-surround network.
On-center, off-surround, like in vision.
Similar principle, yes. Imagine your expectations setting up a filter. It provides an excitatory bias, the on-center, to neurons representing features it anticipates, making them easier to activate, while simultaneously providing inhibitory signals, the off-surround, to neurons representing features that are irrelevant or contradict the expectation, making them harder to activate. It's like turning up the gain on what you expect and turning down the gain on everything else.
And this specific structure, an on-center, off-surround feedback loop, is that something neuroscientists actually see in the brain? Is there evidence?
Yes. The source highlights that this has anatomical and neurophysiological support. Experimentalists often refer to this kind of dynamic as biased competition.
Biased competition, right.
There's evidence for these kinds of modulatory effects and gain amplification of matched signals in circuits like the feedback pathways from visual cortex, V1, back to the thalamus, LGN, or in auditory cortex, the wiring seems to be there.
Okay, so top-down expectations usually modulate activity, helping you see what you're looking for. But the article talks about a scenario where these expectations can actually generate activity directly, even without strong bottom-up input.
Right. The theory suggests that under certain conditions, possibly driven by volitional signals, maybe from the basal ganglia, for instance, this can shift.
How so?
If these top-down signals are strong enough, or if they maybe inhibit local inhibitory neurons, they can cause neurons in the feature layer to fire directly, even without strong sensory input coming in from the outside world.
And what does that capability give us? Why would the brain do that?
That's how the brain can generate internal representations, mental imagery, and planning.
Seeing things in your mind's eye.
Exactly. You can activate expected patterns internally to explore possibilities or run simulations in your head, essentially doing prediction without action. It's a powerful cognitive tool that offers significant evolutionary advantages, obviously.
But then the source makes this kind of startling connection. What happens if that control mechanism goes awry, if it becomes overactive?
That's where the theory gets really interesting, and maybe a bit speculative, but thought-provoking. It suggests that if those volitional control signals become pathologically hyperactive or imbalanced, those top-down expectations could start firing neurons spontaneously, creating patterns even when there's no bottom-up input to match or constrain them.
And that would feel like?
This could potentially manifest as phenomena like hallucinations. It offers a theoretical link emerging from the basic RT circuitry to a complex symptom seen in conditions like schizophrenia.
Wow, that's quite a leap from how we simply recognize objects to potentially explaining hallucinations based on the same core mechanisms.
It shows the potential explanatory power of the framework.
Okay. So far, we've mostly discussed how our key handles inputs that are familiar or match a learned category well enough to resonate. But what happens when something is truly novel? If learning relies on a good match leading to resonance, how do we learn things we've never encountered before? There's no existing category to match.
That's where the second crucial component comes in. The interaction between the attentional system, where matching and resonance happen, and a complementary orienting system.
An orienting system, what does that do?
The orienting system is designed specifically to be sensitive to unexpected, unfamiliar, or novel events, things that don't fit.
And based on the source, where is this orienting system thought to be located in the brain? Any ideas?
It's hypothesized to involve areas like the nonspecific thalamus and the hippocampal system, areas known to be involved in novelty detection and memory formation.
Okay, so if the attentional system gets input that doesn't match any learned category very well, it signals the orienting system. Help, this doesn't fit.
Exactly. A significant mismatch between the incoming bottom-up pattern and the top-down expectation generated by the initially chosen category activates the orienting system, a sort of prediction error signal.
And what's the orienting system's response? What does it do when it gets that signal?
Because the orienting system's primary job is detecting novelty or mismatch, not identifying what the input is, it sends a burst of non-specific arousal back to the attentional system.
Non-specific arousal,
Yeah.
like a jolt.
Yeah, a global pay attention, something unusual is happening signal. As the source puts it, novel events are arousing. It wakes the system up.
That makes perfect sense from a survival perspective. Something new or unexpected happens and bang, you get a jolt of attention. But how does that arousal help the system learn the novel input? What's the next step?
This arousal burst, combined with properties of what RT calls medium-term memory, MTM, specifically habituative gates, think of connections that temporarily weaken with recent activity.
Okay, like they get tired.
Kind of, yeah. That combination causes the currently active recognition category, the one that generated the poor expectation, to be reset or inhibited. It's like the system saying, okay, that hypothesis didn't work, clear the board, try again.
So the wrong answer gets shut down.
Yeah.
Then what happens? Does it just give up?
No, resetting the current category triggers a memory search, or what you could call hypothesis testing.
Okay.
The attentional system then rapidly searches through other learned categories to see if any of them provide a better match for the input pattern.
So it tries other possibilities.
Right. This cycle resonance, attempted match, mismatch reset if the match is poor, and search continues.
Until it finds a good enough match with an existing category.
Or
What if nothing fits?
if the input is truly novel and doesn't fit any existing category adequately, the search process will automatically select an as-yet uncommitted category, essentially. A blank slate, a node in the network, ready to be trained.
Ah, so it grabs some unused memory space to learn the new thing.
Precisely.
And once a good match is found, or a new category is selected for a novel input, what happens then?
Then resonance occurs with that chosen category, either the existing one that finally matched or the newly selected uncommitted one. And remember,
Only resonance drives learning.
exactly. So this final resonance with the correct established category or the newly selected uncommitted category triggers the stable learning of the adaptive weights and the top-down expectation for that pattern. The novel information has now been successfully integrated into the system's memory.
Wow. That reset search cycle, driven by the orienting system when there's a predictive mismatch, is really the key to how art allows for continuous learning in a non-stationary world without wiping out old memories.
It is.
It ensures stability unless there's a significant error, in which case it triggers plasticity and search, finds or makes a place for the new info.
It's the core of the RT solution to the stability-plasticity dilemma, that dynamic interplay.
We've talked about learning stable categories, like recognizing faces in general. But there's a difference between knowing face as a general category and recognizing your specific friend's face. How does RT handle that level of detail? How does it control whether it learns broad patterns or fine-grained specifics?
That's controlled by another crucial parameter in this system called vigilance.
Vigilance, like being watchful.
Kind of, yeah. Vigilance acts like a game control that sets the strictness of the matching criterion. It determines how good the match between bottom-up input and top-down expectation needs to be before that orienting system gets triggered and forces a reset in search.
Okay, so if vigilance is low, what happens then?
With low vigilance, the system tolerates larger mismatches. It's more lenient. This allows many slightly different inputs to be grouped into the same category, promoting the learning of broad, general categories and abstract prototypes, like the general concept of dog or chair.
Okay, fuzzy categories.
Yep.
And if vigilance is high...
High vigilance demands a very close match. It's much stricter. Even small differences between the input and the current best matching prototype will trigger a reset and force a search for a new category or the selection of a new uncommitted category.
So high vigilance leads to?
It leads to learning more specific exemplars or more detailed prototypes, like distinguishing different breeds of dogs or recognizing that specific chair in your house, or clearly differentiating between similar letters like E and F where small details matter.
Where does the system get its vigilance setting from? Is it fixed or can it change?
The source states that vigilance is computed in the orienting system. It's based on a comparison between the features in the input that were successfully matched by the top-down expectation versus the total number of features in the original input.
Like a match percentage?
Sort of, yeah. A poor ratio indicates a less than ideal match, and the orienting system can use this to potentially increase vigilance or trigger a reset if the current vigilance level is already high enough to deem the match insufficient.
So vigilance isn't necessarily static, it can adapt.
Exactly. Through a process called match tracking, vigilance can dynamically increase, typically just enough to force a reset and search when a predictive error occurs.
Why would it do that?
Well, this process embodies what RT calls a minimax learning rule. The system aims to maximize category generality, using fewer categories being efficient, while minimizing predictive error.
Get it right, but be as general as possible.
Exactly. Be as general as possible, but get more specific when necessary to correctly classify inputs and avoid errors.
That makes a lot of sense. You want to be efficient and general, but precise when the world demands it. And the article links this process to memory consolidation. How does that work?
Yes, it notes that as learning progresses and adaptive weights stabilize, familiar inputs can eventually bypass the search process entirely and directly access the best matching category, leading to faster recognition. No more searching needed for things you know well.
Oh, okay. Like muscle memory for recognition.
In a way, this dynamic is consistent with aspects of memory consolidation, and the theory suggests that disruptions in this process, perhaps due to damage to the hippocampal-based orienting system, which helps drive search, could contribute to symptoms seen in medial temporal amnesia.
Interesting connection. And there's this point that the learned connections in these RT models can actually be interpreted as fuzzy if-then rules. That seems counterintuitive for neural networks.
Yes, it's a significant finding mentioned in the source. It shows that these seemingly complex neural network dynamics can actually learn rule-based behaviors, countering the older idea that neural networks are always just opaque black boxes or incapable of rule extraction. You can sometimes see the logic emerge.
So this whole theory is built on foundational mathematical equations describing how different types of memory interact. STM, LTM.
That forms the underlying framework equations for short-term memory, STM, like holding things in mind, medium-term memory, MTM, those habituative gates involved in search, and long-term memory, LTM, the learned weights, specialized for different brain systems.
Great.
And the principles of RT have been extended beyond just the abstract model to consider how they could be physically realized within the layered structure of the cerebral cortex.
You mean like mapping RT mechanisms onto the actual 6 layers of the cortex? That sounds ambitious.
Exactly. This is the domain of laminar computing. It's a research effort aiming to show how theoretical principles like RT can be implemented in the actual circuit architecture of the brain, unifying different research areas like category learning and visual perception within a common cortical framework.
Are there specific models based on this, concrete examples?
Yes, the source mentions examples like Laminart for visual processing, Cartword for speech and language processing, and ListParse for cognitive processing and working memory.
Okay.
These are computational models that simulate specific brain areas and functions based on art principles realized in these layered laminar circuits.
And the theory even connects to the timing of brain activity, like brain waves or oscillations.
Yes, models like SMART, which use more biologically realistic spiking neurons, make concrete predictions about brain rhythms.
Such as?
They predict that the resonance states, which, remember, drive learning, are associated with fast gamma oscillations, high-frequency activity.
Okay, gamma for learning.
In contrast, the mismatch signals and reset processes, which prevent learning of incorrect associations, are linked to slower beta oscillations.
And beta for reset or mismatch? Is there evidence for that prediction? Do we see that in brains?
The source points to supporting data showing these gamma-beta dynamics linked to match-mismatch processes in areas like visual cortex, hippocampus, and frontal eye fields during tasks involving attention and learning.
So the theory bridges multiple levels of analysis, from abstract computational principles down to the specific timing of neural firing and brain rhythms. That's pretty comprehensive.
That's the goal, a unified, multi-level account of how the brain learns and processes information. The source also reinforces the neurobiological connections we've touched on throughout, linking RT mechanisms to specific brain regions like different areas of the cortex, the thalamus, hippocampus, prefrontal cortex, basal ganglia, and the nucleus basalis.
Speaking of the nucleus basalis, the article makes that fascinating link about vigilance being potentially controlled by neurotransmitters. Can you remind us about that?
It does. It proposes that the vigilance parameter can be modulated by acetylcholine, released under the influence of the nucleus basalis.
Acetylcholine,
Yeah.
involved in attention and memory, right?
Right. Exactly. This nucleus is thought to be activated by predictive errors or novelty, and increasing ASTA might then promote higher vigilance, encouraging the system to search for finer categories or pay more attention to detail, even if a coarse match already exists. It basically tells the system, be more careful, look closer.
And that's where the potential connection to autism comes in. How does that work?
Yes, the source notes the intriguing prediction that a state of chronically high vigilance, perhaps due to abnormalities in the cholinergic system involving the nucleus basalis, could contribute to some of the symptoms seen in certain individuals with autism.
Like what kind of symptoms?
This includes phenomena like hyperspecific learning, an intense focus on details sometimes at the expense of the bigger picture, or certain attentional difficulties. The source mentions supporting psychophysical data and anatomical findings consistent with cholinergic system differences in autism.
That's a powerful way. A theoretical parameter like vigilance could potentially shed light on a complex condition like autism. It's not just about explaining typical learning.
Right. It suggests how variations in these core mechanisms might lead to different cognitive profiles.
Beyond understanding the brain itself, RT principles have also had a significant impact on technology and engineering, right? It's not just theoretical.
Absolutely. The principles developed in art, because they deal with stable learning in changing environments, have led to a family of algorithms that are widely used in applied settings.
What kind of real-world applications are we talking about?
The source lists diverse examples like medical data analysis and prediction, remote sensing, analyzing satellite images, for instance, optimizing airplane design, and guiding robotic systems that need to adapt to unpredictable situations.
Wow. And are there specific algorithms people use?
Yes, algorithms derived from art, like different art SMATE variants, fuzzy art, and others, are used globally by researchers and engineers for tasks like classification, clustering, pattern recognition, especially where data might arrive sequentially and needs to be learned online without forgetting past data.
So it's not just a theory for understanding the brain. It's also become a framework for building intelligent systems that face similar challenges out there in the real world.
Precisely. It's a testament, I think, to the value of building theories grounded in fundamental principles and neurobiological insights. The brain's solutions can inspire better technology.
Wow, we've really journeyed from a basic puzzle about learning how not to forget things to a theory that touches on consciousness, attention, specific brain circuits, neurotransmitters, and real-world tech.
We started with the stability-plasticity dilemma, how to learn fast without forgetting the past, that fundamental tension.
And we saw how adaptive resonance theory proposes a solution built on the interaction of attention and an orienting system,
Right.
using match-based learning driven by resonance for stability and mismatch-based reset and search for handling novelty and promoting necessary plasticity.
We explored the core idea that conscious states might be resonance states, linking internal brain dynamics to our subjective experience, and how the complementary what and where processing streams handle different types of memory, declarative versus procedural.
And we discussed how a parameter like vigilance controls the generality of learning, how specific or broad our categories become,
Uh-huh.
potentially linked to brain chemistry like acetylcholine,
Mhm.
and even offering insights into conditions like autism, before touching on how RD principles are being mapped onto the brain's layered structure and applied in technology.
It provides a really comprehensive framework for thinking about how your brain manages that constant flood of information, balancing the need to build stable knowledge with the need to adapt to a constantly changing world.
Yeah.
It offers, I think, a fascinating window into the mechanics behind attention, memory formation, and maybe even the nature of conscious perception itself.
Thinking about RT's framework, especially that interaction between mismatch, reset, and the search for a novel, resonant connection. Here's something to ponder. What does this imply about those moments when you suddenly get something, an aha moment?
Interesting question.
Or even creativity itself?
Yeah.
Could they be moments where the system has been stuck in a state of mismatch and search, maybe unconsciously, and then suddenly finds a resonant connection, perhaps a connection that was previously hidden, or between seemingly unrelated ideas?
That's a fascinating thought, resonance as the basis for insight.
Or, thinking about vigilance, how much does our own internal vigilance setting, maybe influenced by mood, fatigue, or even personality, influence what we notice day to day, what we learn in detail versus what we just categorize broadly? It makes you think about the subtle, complex dance of attention and memory happening beneath the surface of every single learning experience.